I'm going to tell you the story of the Big Bang. I'm going to tell you the story of 13.78 billion years, and I'll try and squeeze it into about 25 minutes. One thing to say is there's going to be a particular focus in this talk, which I think is kind of important. What I want to focus on is really sort of making clear what parts of the story are just right, what parts of the story that we've got nailed and we're absolutely sure are true, and what parts of the story we think are probably right, we think we're on the right track, but we're not sure about, and what parts of the story are just completely speculative and maybe wildly wrong. And I think this is important because certainly when I read the popular literature, I get the feeling that the lines between these things are just completely blurred, that there's just no distinction made between what's real science that's been confirmed and things that just are fantasies of people's imagination. So I really just want to try and put this, delineate the differences between these. Okay, good. See if I can figure out how this works. Perfect. I'm going to start at the beginning. And as you all know, in the beginning, there was a Big Bang. Except there wasn't. This is not what the beginning of the universe looked like. There was no bang in the Big Bang Theory. There's no explosion in the Big Bang Theory. In fact, and this may come as a bit of a surprise, the Big Bang Theory has absolutely nothing to say about the question of how the universe started. Okay. There's a very simple answer to the question of how did the universe start, which is that we don't know. We haven't got the slightest idea what happened at the very beginning, which is just beyond our current knowledge. I hope very much it's something that science will get to at some point, but at the moment it's not something that we understand in the slightest. So what the Big Bang Theory does tell us about, what it does describe, is what the universe looked like when it was very much younger. And the entire theory is based on an extremely simple premise. It's the following. We look out in the universe around us, and we see all the stars and the galaxies, and all of those galaxies are moving further away. So tomorrow they're going to be further away from each other than they are today. The Big Bang Theory really just winds the clock back and makes the very obvious observation that if you go back into the past, everything's closer together. So the Big Bang Theory takes that and just pushes it to the most extreme limit imaginable. It suggests the following. As you squeeze things closer together, they get hotter. And the Big Bang Theory says that if you take that to the limit, there was a time in the very distant past, it's about 14 billion years ago, when there were no stars, there were no galaxies, there were no planets. Instead, the entire universe was filled with a fireball. And that's really the essence of the Big Bang Theory. It doesn't say what happened right at the beginning, it just says that in the early days of the universe, there was a fireball that filled all of space. And the details of the Big Bang Theory are all about figuring out what was happening in the fireball and what the consequences of that fireball were for the future evolution of the universe. Okay, so that's the story I want to tell you about, and in particular the story of that fireball. Let me just sort of give you a pictorial view of what's going on here. This is the entire universe. This is the history of history itself. You should think about this as, this sort of white blurry bit here is what we would colloquially call the Big Bang. So this is what I've already said, the point of creation or whatever it is. It's the thing that we don't understand anything about at all. Okay, it's sort of why it's blurry in this picture. So this is the beginning of the universe that we don't understand, and then time runs this way in the picture, and so you can see that for the first, and I'll just point, you can see that for the first period of the universe, there was a fireball which filled the universe. This is this kind of mottled green and blue color in the diagram here, and this is what I'm mostly going to talk about throughout the talk. Okay. But at some point, of course, the fireball cooled, it stopped glowing. This happened at around 380,000 years after the Big Bang. So there was about 380,000 years with this fireball. And then when it cooled, there was a long period where the universe was just really boring. Okay, it's what cosmologists call the Dark Ages. And this is what was going on in the Dark Ages. There was a bunch of stuff. The stuff was more or less just hydrogen atoms. And the hydrogen atoms were just kind of floating around and not doing very much at all. That was all that was happening in the universe. But very slowly, over a long period of time, the hydrogen started to gather and clump together. It did this just because of gravity. Gravity affects everything and attracts everything. So over a long, long period of time, the hydrogen would clump, and there'd be a little clump here forming and a little clump here forming. And then as time went on, these clumps would get bigger and bigger. And as they got bigger, the pressure inside the clump would get larger and larger. Until after about 500 million years of the universe just being boring, the pressure inside the clumps got so large that the hydrogen ignited. This was the birth of the very first stars. And from then on, the universe gets extremely interesting. There are stars being born, there are stars dying. When they die, they have these wonderful supernova explosions. They spew out all these heavy elements that they've created into the void. It forms new stars, it forms galaxies, it forms planets, and at least if you live in an interesting part of the universe, you see evolution of dinosaurs and humans and philosophy festivals and so on. Okay, so that's what's going on. And we understand a lot of what I've just told you. We understand the broad brush details perfectly, but we understand lots of the little details as well from sort of these first stars onwards. And the reason we understand so well is just that we can see it. You build a big enough telescope and you look far enough away. When you look far away, you're looking backwards in time, because the stars that you see in the sky are billions of light years away, which means the light took billions of years to get from the stars to you, and you're looking at them as they were billions of years ago. So the bigger the telescope you build, the further back in time you're looking. And we're kind of at this level now. Okay. That's sort of 13 billion years in 2 minutes. What I want to focus on for the rest of the time is really the very beginning, what was happening in the fireball. And there's a very natural question which you should ask about this fireball, which is the following. How can we possibly know there was a fireball in the universe 13.5 billion years ago? It just seems like utmost hubris to say that we actually know this. But we do know it. It's just true. And the reason we know it's true is because we can see it. In fact, it's not just that we can see it, we've just taken a photograph of it. So this is the photograph of the fireball that filled the Big Bang in the early universe. It's got a fancy name. It's called the cosmic microwave background radiation. I've noticed that all the newspapers call it first light, which is kind of dramatic. Physicists just called it the CMB. But we should call it what it is. It's a photograph of the Big Bang. It's that simple. Okay? And you can see that this fireball is flickering. There are bits in the fireball that are hot, they're red, and there are bits in the fireball that are cold, they're blue. And there's information in these flickers. In fact, the whole subject is really about what's going on with these flickers, as I'll explain later. Let me just give you an analogy for this. If you sit in a campfire and you stare at the flames, you see the flames flickering. But if you stare close enough at the flames and you analyze those flickers, you do spectroscopic analysis or something, you can figure out what's burning in the fire just by looking at the flames. You can tell if it's wood or if it's coal or if it's paper or what kind of wood it is. You can understand what's happening just with the flickering in the flames of a campfire. And the same is true here. If we can understand these flickerings, we can understand what was going on in the fireball that filled the universe at the beginning of time. Okay, so that's the story that we're going to tell. Okay, so what's going on? I'm going to spend the next 5 minutes telling you a little bit more about this fireball, because it lasted 380,000 years. It's quite a long time. And during that 380,000 years, this fireball was changing. It was evolving in different ways. So I just want to tell you how it was evolving. Here's the punchline. The punchline is really straightforward. As you go backwards in time, the fireball gets hotter. And as the fireball gets hotter, more and more stuff melts. Okay, that's sort of the punchline. I should warn you that the next 5 minutes are kind of going to be a little bit like the following. I'm going to be saying, and at this time this happened, and at this time this happened, and at this time this happened. And, there'll be lots of details, but it's too much. After 5 minutes, I'm going to give you kind of an overall picture. Okay, so that's where we're going. Okay, let's start at the end of the fireball. The end of the fireball, as I said, 380,000 years after the Big Bang. At this time, the fireball is roughly 100,000 degrees centigrade. Okay, it's fairly hot. It's not crazy hot. It's fairly hot. Give you some idea, surface of the sun, 6,000 degrees centigrade. So it's hotter than the surface of the sun. It's a hot place. What happens at 100,000 degrees centigrade is the following. Atoms melt. So I'll explain what I mean by this. As we all know, an atom is a nucleus, and the nucleus contains protons and neutrons, and then there are electrons which orbit the nucleus, at least in this kind of cartoon picture here. Okay? At 100,000 degrees centigrade, the electrons just can't cling on anymore, so they get stripped away from the nucleus of the atom. So at this temperature, what you have is a gas, not of atoms, but a gas of the nuclei, and then electrons which are flying around. Okay? It's usually called a plasma rather than a gas. So that's what's going on. So that's 380,000 years, and now we wind the clock back. And as we go backwards in time, things get hotter. And the first thing that happens is everything just speeds up. That's what happens when you increase the temperature. Everything flies around much, much faster. And other than that, not much more happens until you reach a temperature, let me get this right, of 10,000 million Celsius. Okay, that's 10 to the 10 degrees. It takes a long time for things to get that hot, long time going backwards. You reach this temperature only when you get to 1/100th of a second after the Big Bang itself. Okay? But 1/100th of a second after the Big Bang, you hit this temperature. At this temperature, nuclei melt. That means that the nuclei contain protons and neutrons, but when you hit this temperature, they fall apart into just protons and neutrons. They can't stick together anymore. Okay? That's 1/100th of a second after the Big Bang. Then we go further back in time until we reach 1/1,000,000th of a second after the Big Bang. 1/1,000,000th of a second after the Big Bang, the temperature is 10 to the 13 degrees, and now the protons and neutrons melt. So what does that mean? Protons and neutrons each have 3 quarks inside them. When you get to 1/1,000,000th of a second after the Big Bang, those quarks kind of fall apart from inside the proton and neutron. They're no longer stuck together anymore. Okay? This already sounds kind of preposterous, but we can go further back. There's one more step where we really understand what's happening, which is when you get to 1/1,000,000th of a millionth of a second after the Big Bang. It's about 10 to the minus 11 seconds, to be precise. When you get to 1/1,000,000th of a millionth of a second after the Big Bang, the Higgs boson melts. So you've probably all heard we discovered the Higgs boson finally last summer. I've put melts in inverted commas here. As far as we know, there's nothing inside the Higgs boson, so that's not what I mean. Instead, what happens is the Higgs boson just stops working. So the Higgs boson plays a role in our universe, which is that all the other particles have mass because of the presence of the Higgs boson. When you reach these temperatures, it just doesn't do that anymore. So at these temperatures, the Higgs boson stops giving mass to everything else, and all the other particles that are floating around suddenly become really kind of light and breezy, and they fly around. Okay. Okay, so I told you it would be like detail after detail after detail. Here's the deal. You know, this sounds ridiculous. This is 1/1,000,000th of a second after the Big Bang, and I'm telling you exactly what happened. But this is the stuff that we're sure happened, that we just know about. And I'd like to explain why. It's because all of the things that I've listed here, to one degree or another, we can recreate here on Earth. We can just get these conditions and make them here on Earth, make mini Big Bangs here on Earth. So let me give you one example. This third thing, where protons and neutrons melt. We finally achieved this 12 years ago in a place called Brookhaven in Long Island, just outside of New York City. And what these guys did was just amazing. They took gold atoms and they heated them up to this temperature. I don't even know what it is, like a gazillion degrees centigrade. And at that temperature, they saw that protons and neutrons inside the nucleus of the gold atom melt. And the quarks that are inside them fall apart. I should stress, these quarks don't come outside of protons and neutrons naturally. They've been trapped there for 14 billion years, since the beginning of time itself, but at last, in Long Island, New York, for the first time since the Big Bang, they were liberated. The same is true of the Higgs boson. I mean, we're, to a slightly less degree, I should confess. We've discovered the Higgs boson last year. We haven't quite pushed it to these limits yet, but we have a theory which is working absolutely perfectly for the Higgs boson. It just passes every test, and within the next years and decades, we're going to start pushing the limits of what we see here. So that's why we think we understand the Big Bang at this level. It's because we can recreate these situations here on Earth. We can develop theories which work perfectly for these situations. And then we take those theories and just import them to the Big Bang, where we see that they just fit all the observations perfectly there as well. So this is what we trust about the early universe. And it's not bad, right? It's a millionth of a millionth second after the Big Bang, and I'm standing here telling you that we just know this is what happened. But it's not enough. It's a millionth of a second, but that's a lifetime if you're a subatomic particle. There's so many interesting things that can happen in a millionth of a second that we still need to understand. So that's where we want to go next. So this is kind of the end of exactly what we know happened. And from now on, things get a little more speculative. Okay? Okay, so what's the next step? Well, there's a reason, even though we don't have theories, we don't have a good theory to understand that first millionth of a second, there's a really good reason to suspect that we can figure it out. And it's the following. That all of these ripples and fluctuations and flickering that we see in the fireball, everything I've explained to you so far, all of that melting and quarks and Higgs boson stuff, none of that can explain those flickerings. So whatever caused the flickerings in the fireball definitely happened in the first millionth of a second of the Big Bang. So we don't have a theory. We don't know what theory applies here. It's not something we can recreate on Earth, but we've got a damn good clue about what we should be looking for, because we've got a picture, literally a photograph of what happened, what must have happened in that time. So that's the challenge. That's the challenge for theoretical physics. It's to cook up a theory which explains perfectly these flickerings that we see here. Okay. And we think we know the answer. So now we're kind of in the level where we're fairly sure, but we think we know the answer. So this is what we believe happened. We believe the answer is something called inflation. Now, inflation was proposed in the 1980s by a guy called Alan Guth. When it was proposed, it had nothing whatsoever to do with these ripples, these flickerings. In fact, these hadn't even been measured at the time in the 1980s. It was instead a theory which was proposed to solve various other problems that arise in the Big Bang theory of cosmology, and it solved all those problems. It made a few experimental predictions, all of which turned out to be correct. So it's kind of ticking all the boxes of things you want from a scientific theory. And then later, it was realized that this theory of inflation reproduced these ripples. So let me tell you firstly what the theory of inflation is. I should tell you, it sounds stupid, it sounds preposterous. The theory of inflation says that in the first millionth of a second, the universe expanded very, very quickly. Okay? Very, very is a technical word. Very, very here means that in a millionth of a second, the universe doubled a million times. Okay? 10 to the power 60 was how much the universe expanded in that short time. Okay, it sounds stupid, but that's the theory. Let me tell you how it gives rise to these ripples. Let me tell you why it gives rise to something like this. On the very smallest scales of the universe, everything is governed by quantum mechanics. Quantum mechanics is randomness and probability. And if you take even empty space, just take empty space and look close into empty space, you'll see that this randomness of quantum mechanics has an effect, because empty space isn't empty. What happens are particles and antiparticles kind of pop out of the vacuum, and then they swim around for a bit, and then they annihilate again, and then they come out, and they go back down. So even empty space is sort of a soup of this quantum random stuff at small distances, constantly bubbling up and down. And this isn't science fiction. This is our best theories predict this, and it's been measured, this random soup of stuff. Okay, this is what inflation does. On very small scales, there's all this quantum randomness. But inflation makes the universe grow dramatically in a short space of time. And it kind of catches these quantum fluctuations in the act. So they fluctuated, and there was some random stuff. And in the time before they can fluctuate back, inflation has suddenly blown these things up to enormous sizes that stretch across the entire sky, the entire universe. So that's what we think this picture is a picture of. We think it's a picture of the quantum randomness of particles and space-time in the first millionth of a second after the Big Bang. Okay? We think we've taken a photograph of it. Sounds extraordinary. If that's not extraordinary enough, there's more to this story, which is the following. Remember I told you that after the fireball cools down, there's this boring time when hydrogen is clumping and stars are forming. That hydrogen doesn't clump in random places. The thing that determines where the hydrogen clumps are the cold spots in this fireball. Because the bits that were hotter in the fireball is where the hydrogen sort of gets pushed out from. So it gets pushed into these cold spots of the fireball. So where the first stars and the first galaxies formed is where the cold spots were in this fireball. We can do the following. We can just look through telescopes out at all the galaxies in the universe and make a big 3D map of where galaxies are in the universe. And then we can look at the patterns of those galaxies, and we can see that the pattern matches the pattern on this picture. So not precisely, but there's a correlation. There's a correlation between where galaxies are now in our universe and the picture that you're seeing here. So the story I want to tell you, I think it's like one of the greatest stories of all time, is that where the galaxies are in the universe, on the very biggest scale, they have their origin in these small quantum fluctuations that happened in the first millionth of a second after the Big Bang. Where we live, our Milky Way, is somewhere where randomly there was a small little fluctuation one way or another back 13.78 billion years ago. And this isn't science fiction. It sounds like it. This is stuff that we're fairly sure about. I should sort of tell you sociologically what's going on. I think there's a consensus among about 90% of cosmologists that this is the correct story. There's a very vocal 10% that disagree strongly that this is the story. But in my field of theoretical physics, everybody disagrees with everybody else. Having 90% it's not bad, actually. So that's kind of the level we're at with understanding inflation. Okay, good. But of course, we want to understand more than this, right? So now comes the next step. And the next step is, what on earth caused inflation? This universe just grew a million, whatever it was, times, and something must have been pushing it. Something must have been making this happen. So that's the next thing we'd like to understand. Why did inflation happen? So here we get to the level of just speculative ideas. We don't know what caused inflation to happen, but we do have lots of ideas. So of all the ideas that are out there, there's quite a lot, I'm just going to tell you about mine. So about 10 years ago, I was working with a couple of friends. We had an idea about what could cause inflation. And I got to say, I thought it was a brilliant idea. It had all that sexy stuff that science is supposed to have. There was string theory, and there was extra dimensions, and there was kind of our universe, and then our universe slipped sidewards into one of those extra dimensions, and we could show that when it slipped, it gave rise to inflation, and it just sounded sexy, it sounded interesting. We just thought it was fantastic. This all took place, by the way, 10 to the minus 35 seconds after the Big Bang. So it's a millionth of a millionth of a millionth of a millionth of it's silly times, right? So what happened? It's really easy to have sexy ideas in physics. What's hard is to figure out the consequences of those ideas. So we worked for, I don't know, maybe 6 months, maybe a year, doing calculations, trying to figure out that if this happened, what would we see? What would we see in the universe now? And we discovered something really nice. We discovered that those ripples that we see in the fireball would be just like all theories of inflation predict, would be as they are. But we found that if you look close enough, if you get a picture of that fireball at high enough resolution, there will be some extra details etched into it. Okay. And what's more, the resolution you had to get to was the resolution that a satellite called the Planck satellite would see. Now, the Planck satellite flew in 2009. We did this work in 2001. Planck satellite flew in 2009. And on March 21st this year, it released its picture of the Big Bang to the general scientific public. So obviously I was a bit interested in what this picture would show. And what it showed, I should say that the Planck satellite had a team looking for exactly the signal that I had predicted. It was sort of a broader signal. What it showed was that the signal isn't there. What it showed is that my theory is just wrong. I'm being a bit harsh on myself here. My theory is hanging by a thread, I think is a better way of saying it. But it sounds more dramatic to say it's wrong. So we don't know what the current theory is that caused inflation at this silly time. But what I find absolutely remarkable is that this is a theory that operates in the first 10 to the minus 35 seconds of the universe, and it's experimentally falsifiable. Okay, it's not just experimentally falsifiable, this one's experimentally falsified. That's kind of remarkable, I think. That's really sort of setting a new bar for where science gets to. So, I don't feel too bad about being wrong. It would have been nice to be right, but I'll be right about other things. It's okay. What I want to really get across here is just that we don't know what caused inflation, but, and I hope this is clear, we're going to find out. This is strictly within the sights of empirical science to figure out what happened 10 to the minus 35 seconds after the Big Bang. We don't know yet, but we're going to get there. To finish, there's a guy at the back saying I do have t equals 0, so let me just briefly touch upon the ultimate question. What really happened at the Big Bang itself? What kick-started it all off? As I said at the beginning of the talk, we really don't have any ideas. It's almost true. There are lots of ideas. I think there are just no good ideas. So we really need to work much harder to understand this question. I think we can do it. I don't know if it's going to be in my lifetime, but I certainly think that with a bit of creativity, this is something that we can hope to address with some interesting new theories and the new experimental data that's going to be coming. Okay, I think I'm going to finish there. Thank you very much.